Okay, so we are taking a brief look at thermodynamics. This video goes along with activity 1.3.3 thermodynamics, and it will be split up into more than one video. So this one is going to serve for you to get through questions number 1 through 17 for activity 1.3.3. So again, welcome to the introduction to thermodynamics. Now do yourself a favor, not anywhere near me, but rub your hands together for 15 seconds. What do you notice about that? After you've done that for 15 seconds, have you noticed that your hands are warm? The reason that they're warm is because of a transfer of energy into the form of thermal energy. Thermodynamics is the study of the effects of work, heat, and energy on a system. Put another way, nothing happens without heat flow. Thermodynamics is the science of the relationship between heat, work, temperature, and energy. In broad terms, thermodynamics deals with the transfer of energy from one place to another and from one form of energy to another form of energy. The key concept here is that heat is a form of energy that corresponds to a definite amount of mechanical work. Heat was not formally recognized as a form of energy until about 1798, when Count Rumford, a British military engineer, noticed that limitless amounts of heat could be generated in the boring of cannon barrels. And that amount of heat generated is proportional to the work done in the turning of the blunt boring tool. These observations of the proportionality between heat generated and work done lies at the foundation of thermodynamics. Thermodynamic systems are part of the physical world as described by its thermodynamic properties like temperature, volume, pressure, concentration, surface tension, and viscosity. Examples of thermodynamic systems are washing machines, refrigerators, and air conditioners. Air conditioners are considered a closed system that circulates refrigerant inside of the system, altering the pressure of the refrigerant at different points to promote heat transfer. A refrigerator is an open system that absorbs heat from a closed space and passes it to a warmer area. To better understand thermodynamics, we need to cover the differences between thermal energy and temperature. Thermal energy is defined as the kinetic energy in transit from one object to another due to a temperature difference, and it is measured in joules. It's the flow of energy, usually heat, from having a temperature difference between two objects. Temperature, on the other hand, is the average kinetic energy of particles within an object, not the total amount of kinetic energy particles, and it is measured in degrees. So temperature describes the average kinetic energy of the particles of an object. It is a measurable physical characteristic of an object. And we measure it in degrees Celsius, degrees Fahrenheit, in kelvins, or in Rankine. If you take a look at this image right here, they're showing you an object temperature with a temperature of a random temperature. As you can see from their thermometer here, it looks like it's a little bit warmer than temperature number 2 of this object. And we see that the thermal energy, that heat transfer, is going from object 1 to object 2. As I mentioned before, we have different temperature scales. Something to keep in mind is that when we look at matter, all matter is made up of molecules, and those molecules are in motion. And you guys know this from middle school. All matter is made up of molecules. If you are a solid, your particles, your molecules are stuck in place, but they have some amount of kinetic energy. They're able to vibrate back and forth. A liquid has particles that are capable of moving. They can slide past each other, but they're still attracted to one another. Gases, when we talk about those molecules that are in motion, are free to move within the container. There is no attraction anymore. Now, to go from a solid to a liquid and to a gas, we have to do what? You have to increase the amount of kinetic energy. We have to increase the amount of energy going into it. And a lot of ways, it's by increasing thermal energy. If like when I think about a solid block of water, what is a solid block of water, by the way? Yeah, it's ice. When you take that solid block of water and you want to take it and get those particles to move faster and become a liquid, you have to introduce energy to it. Typically, that energy is going to be thermal energy, like I mentioned before. If you want to take your liquid water and make it into a solid again, you have to take away that motion, and we see a decrease in temperature. All right, popping back up here. Here are some temperature scales that we are going to be working with. Degrees Celsius is 0 degree. Oh, sorry. In Celsius, your freezing point of water is 0. Boiling point is 100. Fahrenheit, which is what we're used to for in terms of temperature outside in the U.S., has a freezing point of water at 32 degrees Fahrenheit, but the boiling point is at 212 degrees Fahrenheit. There are conversions that you can find on the formula sheet to go back and forth between these things. And then we have kelvins. Kelvins is a primary unit of temperature for engineering as well as in the physical sciences. In kelvins, you have 273 is the freezing point of water, and the boiling point of water is 373 kelvins. Something else that I need to point out that is extremely important for us is that 0 kelvins is defined as absolute zero, and this is the point at which there is zero particle motion. So the amount of kinetic energy is completely gone. Those particles are not moving at all, and that's at 0 kelvins, also known as absolute zero. On the degrees Celsius scale, that's at negative 273 degrees. All right, so thermal energy is that transfer of energy from areas of higher temperature to areas of a lower temperature. Again, it's for the transfer between having a difference between two objects. Like all systems, they strive to reach equilibrium, and you guys should be familiar with that term, equilibrium, meaning equal. Thermal equilibrium is defined as when objects within a system have reached the exact same temperature. When thermal equilibrium is reached, the system loses its ability to do any work, to be able to transfer energy. And that brings us to what's known as the 0th law of thermodynamics. This law states that if two systems are separately found to be in thermal equilibrium with a third system, the first two systems are in thermal equilibrium with each other, so all three systems are at that same temperature. Put another way, the big thing here is that there is no heat flow between objects if those objects have the same temperature. This probably seems pretty much like common knowledge to you at this point, but that is the 0th law of thermodynamics. All right, so how do we have energy transferred within a system? Thermal energy or heat transfer is the transfer of movement of thermal energy. The most common types of transfer are going to be convection. Convection is the process by which, in a fluid being heated, the warmer part of the mass rises and your cooler portion sinks. If the heat source is stationary, then you have convection cells that can develop as the rising warm fluid cools and then sinks in regions on either side of the axis of rising. Put in another way, Convection is the transfer of heat energy occurring by movement of currents. This typically occurs in a gas or a liquid state. We are going to talk about convection currents very soon, but you guys are probably familiar with convection currents when you go to heat up water on this on a stove top. The bottom of the water gets hot, it's going to rise, and as it cools, it spreads out and then sinks again. It has to do with the change of density. You may also be familiar with convection currents when it comes to the mantle and the motion of the mantle. As that mantle rock gets heated and becomes more elastic and has that motion where it will rise up towards the surface of the earth, cools off as it gets away from the core, and then sinks back down because as that temperature changes, as it cools down, it becomes more dense. And so we have these convection currents, and that's what leads to the movement of plates on top of the surface of the earth. Wow, I am so sorry. I didn't mean to go on. Conduction is another type of heat transfer that we can see happen. This is when the transfer of heat within an object or between objects occurs by molecular activity without any net external motion. This transfer of heat works better in solids than in liquids. Put another way, conduction is the transfer of heat by the movement of warm matter. For example, a metal spoon placed in a hot cup of soup will feel warm to your hands because the heat from the soup is conducted through the spoon. Then we have radiation, our third common type of thermal energy transfer. Radiation is a process by which energy is transmitted through a medium, like empty space, as electromagnetic waves. This energy travels at the speed of light. This is also referred to as electromagnetic radiation, or EM, capital E, capital M radiation, which is one of the most common examples being the heat that's transferred from the sun to the earth. Not 100% efficiency of this transfer is just not attainable. We've talked about this before, and all of these processes are irreversible. All right, that leads us into our first law of thermodynamics. The first law of thermodynamics states that heat is a form of energy, and the total amount of energy of all kinds in an isolated system is going to be constant. It is an application of the principle of our conservation of energy. So, the law of energy conservation, or the law of conservation of energy, being applied to a thermal system means that energy cannot be created nor destroyed. It is transferred from one object to another object, or it changes form, it changes from one form to another. Thermal energy can be increased within a system by adding thermal energy or heat, or by performing work in a system. The work in a system is a transfer from energy from work that's being done. All right. In addition, some of my extra notes that I have as I did more and more research and went back into my old physics textbooks, when we take a look at the first law of thermodynamics, we need to keep in mind that the internal energy of a system has to be equal to the work that is being done on the system, plus or minus the heat that flows in or out of the system, and any of the other work that is done on the system. Again, this is a restatement of the conservation of energy. Mathematically, this can be calculated by the change of U, which is the change in your internal energy, equaling Q, which is the heat that's added to the system, minus the work that's being done by the system. One example of the first law of thermodynamics is the use of a bicycle pump. When we pump up the tires on a bike or pump up a ball, the bike pump gets hot. It seems that compressing the air inside a pump causes heating. Our arm muscles do work on the gas when we pump the bicycle pump, and the gas heats up. From this, we can develop a relationship between heat, work, and internal energy. First, we need to recognize that the bike pump is a system. The internal energy of the gas in the pump, or the system, has increased because it is hotter by the work done by your muscles on the system, which means that you have a higher internal energy. The change in internal energy of a system, that bike pump, is equal to the energy that's added from the work on the system. The first law of thermodynamics states that the total energy of a system remains constant. Energy can neither be created nor destroyed, rather, it transforms from one form to another. A more common and practical application of the first law is the heat engine. A heat engine converts thermal energy into mechanical energy and vice versa. The basic idea behind the heat engine is using the idea that temperature, volume, and pressure of a gas are related. When a gas is heated, it expands. But if the gas is prevented from expanding, it increases in pressure. The bottom wall of a confinement chamber is the top of a movable piston. This pressure exerts a force on the surface of the piston, causing it to move downwards. This movement can then be harnessed to do work equal to the force that's applied to the top of the piston times the distance the piston moves. Remember, work is equal to force times distance. So again, the movement can be harnessed to do work that's equal to the total force applied to the top of that piston times the distance that that piston moved. All right, our second law of thermodynamics is about the nature of energy. There's a natural tendency of an isolated system to degenerate into a more disordered state. A simple form of the second law of thermodynamics is the idea that thermal energy is going to flow from hot to cold. I always loved this law in college because it made sense to me when I thought about my typical bedroom. So, like, you get your bedroom all cleaned and straightened up, put in a lot of energy, put in a lot of work to fixing everything up so it looks nice. But over time, what is its natural state? Its natural state is to become more disorganized and disordered. They use the example here of when you touch a frozen pizza with your hand, the thermal energy flows in what direction? From the hand to your pizza. And when you touch a cooked pizza with your hand, thermal energy flows in what direction? From the pizza to your hand. All right. To better understand the second law of thermodynamics, we have to include the vocab term entropy. Entropy is the measure of how evenly distributed heat is within a system. Keeping in mind that a system tends to go from order to disorder. Their example that they have here is that firewood has low entropy, where the molecules are in order when stacked, and high entropy when burning. The molecules become more disorderly. The total amount of energy in that world does not change, but the availability of that energy is constantly decreasing. A general statement of the idea that there is a preferred direction for any process is what's covered here with the second law of thermodynamics. This law deals with the variable called entropy, the function of the state of a thermodynamic system whose change in any differential reversible process is equal to the heat absorbed by the system from its surroundings divided by the absolute temperature of the system. Put another way, entropy is a measure of how evenly distributed heat is within the system. All right, so when we look at heat or thermal energy transfer or heat transfer, we mentioned before that there were several different types of heat transfer that can occur, and three are convection, conduction, and radiation. So we're popping back here to convection. Convection is the transfer of thermal energy by movement of fluid, usually a liquid or a gas. Um, when the heat, when the fluid is heated, it expands, becomes less dense, and rises. Heating systems circulate heat throughout a home without the use of pumps through the use of this convection idea. Again, convection is a process by which, when a fluid is being heated, the warmer part of that mass will rise and the cooler portion is going to sink. If the heat source is stationary, convection cells may develop as the rising warm fluid cools and then sinks in regions on either side of the axis of rising. Put another way, convection is the transfer of heat energy occurring by a movement of currents, and again, typically in a gas or a solid state. Again, the mantle and our convection currents is an example. Air at the equator warms up and it rises, it spreads out, becomes less dense, and then sinks. Oh, I'm sorry, becomes more dense and then ends up sinking because it cools. This is how we get wind. This is also how we keep our clouds aloft. A big one that I studied with my master's degree is the convection of ocean currents. Again, you have like cold water coming from the poles that are dense, they sink down, they start to mix with warmer water, they are going to rise up and they bring up the nutrients. So it's a fantastic process right there. All right, so had to take a quick pause there. We're looking at thermal energy transfer. We just discussed convection. Another type is conduction. It's the transfer of thermal energy within an object from molecule to molecule. So a really good comparison would be taking a metal spoon, putting it into a hot bowl of liquid, and that energy transfer, that thermal energy is transferring from the hot liquid to the metal spoon. Eventually, it starts to feel warmer. Let me fix that real quick. Here we go. All right, so the very final little bit that we have for today is taking a look at the thermal energy transfer equations that we are going to be using. So the first one is Q equals mc times delta T. Q is your energy transfer. It needs to be in joules. M is the mass of the material in kilograms. So keep that in mind. A lot of times you're going to be given this in kilograms, and we're going to have to make sure that we change that over to kilograms. I think I just said that wrong. You're going to be given it in grams, and we're going to have to make sure we transfer that into kilograms. C is for the specific heat capacity of a material, and the units there are joules divided by kilograms times your degrees Celsius, your temperature. Something to take note of that is that the specific heat capacity of a material is a known physical property of a material. So we might have to look that information up, but making sure that the units are in joules divided by kilogram times degrees Celsius. Delta T, anytime you see delta, it means a change in, and then the T stands for temperature. In addition, we have the following three equations that we'll be working with as well as we look at how an object in another system or in a system is going to either gain or lose thermal energy. We might be taking a look at the rate of energy transfer, which is our P. Q is the energy transfer that was just mentioned previously. Delta T is going to be change in time, but in seconds. The K is our thermal conductivity for material. A is the area of that material, or literally where that thermal conductivity is coming from. And then L is the thickness of the material. And again, delta T is the difference in temperature. So this is where we are stopping today. The next video, we will calculate it together as a class.